All right, I think we're going to go ahead and get started. So welcome to the first Nano at Tech seminar for 2024. Glad you could be here. Before I introduce today's speaker, just a word. Our next speaker will be on February 13th. That's actually 3 weeks from today. And the speaker will be Professor Suman Datta from Electrical and Computer Engineering. So it's a pleasure to introduce today's speaker, Professor Tequila Harris. Professor Harris got her bachelor's degree in physics at Lane College before going to Rensselaer Polytechnic to get her master's and PhD in mechanical engineering, and then joining Georgia Tech in 2006, where she's currently a professor in the Woodruff School of Mechanical Engineering, and as we were just talking, the director of a laboratory named after her own name that fits with a great acronym. She's won a number of awards, including an NSF Career Award, and it's a pleasure to have her with us today. So I'm going to turn it over to you, Tequila.
Thank you for that lovely introduction, and I'll try to keep myself on time here. All right, I'm assuming everyone can hear me okay, but because I can hear myself. Again, my name is Tequila Harris. Today I'll talk to you a little bit about enabling roll-to-roll manufacture of thin films through conventional and innovative processes. By a show of hands, I'm just trying to get a feel for my audience. How many of you work in spaces where you're processing fluids? You could be spray coating, you could be dip coating. How many of you are familiar with slot die coating? Okay, so we're gonna take a journey because in my group, we focus a lot on slot die coating and various iterations of that, and I'll talk about that a little bit later in one slide. But the tone of today, I'm gonna do a brief introduction, and after that introduction, I will take us through 3 case studies to show the application of the work that we do in my group. Relative to 3 different design concepts, 1 being conventional and 2 being innovative and produced in my group. Thin films are all around us, and they're used in a plethora of different applications, be it energy, flexible electronics, clean water technologies, barrier film. All of those are technically thin film. And they come with different pros and cons in terms of processing, but the devices themselves that are composed of these materials can be very complex or very simple. The simplest case that I can think of quickly is maybe membranes that are used for clean water technology. It's a single material that's made in a wide sheet. You cut it to shape, put it into the system. But there are other technologies, for example, OLEDs, OTIFs, that are a lot more complicated. And when we think about processing these, it's usually using methods that can sometimes be very costly and very expensive because you're doing a combination of things. Sometimes you lay a material down and then you subsequently have to ablate or remove material, which means there's a lot of waste involved. In part, this is because of the technologies that are used. In our world, we tend to, again, make those wide area sheets, single material, and if we wanted a secondary material, we would also ablate. But the key question here for my group is, how can we reduce the manufacturing steps needed to make a product, a film, that performs the way the chemist or the material scientist wants it to, but we can process it at scale. The reason this becomes important is because there's this thing called the Valley of Death. Has anyone heard of this? So, for especially the students, you're working on these cutting edge technologies, you're spending a lot of time, a lot of grit to make things happen in the lab. But ultimately, whatever it is supposed to be used in, you have to be able to scale it up. You have to transition from the university lab scale to commercialization in order for it to be viable. But the problem is, if you are only working with the materials using processes such as spray coating, dip coating, To a lesser degree, Dr. blade extrusion. Guess what? The scalability is reduced significantly. And then whenever you transition to a process that is scalable, the properties change. And it's like, whoa, but this was working in the lab. Why isn't it working now? The reason it's not working now is because there's different shear rates, there are different forces that are applied for each of those processes. And so your structure changes. And so one of our big goals is to figure out how we move from the university research, which takes a lot of resources, and not end up in a valley of death where we don't get to translate the technology, the information, to usable goods. And the easiest way to do this is to go from lab scale to what we call pilot scale, which sits at the intersection of these two areas. But if you think about it, like, well, how do we do that? We don't have pilot scale facilities. Well, there are two ways. One, even for the work that we do in my group, on our roll-to-roll is technically a lab scale roll-to-roll. And so we're showing that various processes are viable and that we can either enhance or maintain the properties that the chemists, material scientists desired using their own platforms. But hopefully at the end of this, I'll show you some new systems that are coming that may excite you as well, because Georgia Tech will have a pilot scale facility to allow us to really look at scaling up from lab scale to pilot, which then easily transitions to commercialization. As a backdrop for this, and to show that even the government worries about this, this was something that was put out by ARPA-E a while back, but there are different stage challenges. So one of them being reproducible manufacturing at the lab scale, reproducible manufacturing at the commercial scale. Look at the time it takes to transition. So just the lab scale runs using pilot scale membranes in this particular case can take anywhere from 1 to 2 years just to figure out if it's feasible, right? So imagine if you're working in tandem then with people who are scaling materials up, and you can test your materials against the spray coating, the dip coating, and the Dr. blade extrusion. We do this. So we work with several people on campus in various capacities. However, I'm not going to be showing that work, but what we have shown is that by integrating and collaborating in this way, not only do we enhance the properties of the materials that they've been creating using different modalities, but we do it faster, we do it cheaper, and sometimes the quality supersedes everything. And so our goal in my research group is to figure out how do we do this. We use experimental, analytical, and numerical methods. This is just a little snippet high level to kind of show you some of the things we do. We go from inception of defects through mitigation steps by showing the process window, the constraint by which you can process without defect, but also we create novel technologies. And so I'm gonna spend most of the time today talking about these things along this lower part of this slide in relationship to roll-to-roll manufacturing. So this is just a little snippet of what that looks like. So we have some material on a roll, we're pulling it from one side to the other, and coating on top of it. So conventional slot die coating. It is composed of a set of plates with a shim in the middle. The shim creates the hole, or the gap, between the two plates. And that's the orifice by which your fluid is flowing. The top of this small die is where you have your inlet. So the fluid flows in, the fluid comes out. What it's coming out onto is, let's say, a piece of PET or a foil, whatever it may be. But you can touch if you want. Sorry, because y'all are eating. I didn't think about that part. But the two halves, so with that you have an inlet flow rate, you have an offset between the dye and that material, and then you have the speed at which the rolls are flowing, well, the rolls are moving. And so the velocity, the flow rate, the standoff height. I'm going to use these terms throughout this talk, and I'll show them a little bit more up close a little bit later. But this process is amazing. It's been around since the 1950s. Kodak is the inventor of it. They used it for film. So we can process a broad range of viscosities. It has very low waste. It processes wide area. It's pre-metered. Pre-metered lets me know that I can control the thickness, I can control the width, ultimately, of the materials that are coming out based on mass conservation alone. But the limitations for more than 50 years, maybe 60, there were not as many advances. There were some where we had flow, where we could stack two materials on top of one another. And in the early 2000s, we also created methods by which we create patches, so patch coating. But for the most part, beyond simple shapes, it's not known for that. The other thing is that it has low resolution. And so whenever you think about how the quality of the film in terms of its resolution, we're talking on the order of 1 millimeter. So we want to advance this. This is one of the spaces. And so the objective of our work was to not only look at the processability of these materials and the quality, but to also advance the technology in a way that allows for more creative deposition. Because if you recall, we're talking about the OTIFs, we're talking about OLEDs. Those structures are very complex. How can we get it? So we created this digital dye that allows for on-off actuation that then allows for depositing fluid in certain regions and potentially creating shapes. And then we could go over that shape and put another coating. And we no longer have to ablate, we no longer have to etch, we literally have the pattern that we desire. The other idea that we had is, can we process more than one fluid? We can get a wide area grade, but it's only one fluid. And so what we were able to do is develop some technology where we demonstrate that we can coat up to 8 different materials simultaneously, maintaining the integrity of the structure by implementing a dye that looks something like this, where you have some inlets, fluid flows down, and you have a nice, beautiful pattern on the surface. So I'm going to talk about all of these as part of 3 case studies. The first one being for fuel cells. Fuel cells are just electrochemical devices that has a membrane in the middle. The material is sometimes, well, it's not sometimes, but it's coated on carbon paper. And this carbon paper can either be directly coated. This is the carbon paper, don't open this one. This one is fine, and you can actually see some of the defects. But the carbon paper, you want me to come this way? You can hold it up to the light, you can see it better, but some of those defects. So we can coat onto PET, we can coat onto porous media. So we can be stable in terms of the material that's deposited. We wanted to make sure that we also have the quality. Here you can see the defects are there. That's literally a Nafion film. But these pinholes and fractures in the material was initially related to chemical degradation, thermal degradation, cycling. For my doctorate, I actually worked with fuel cell materials. My job was to create infrastructure for high temperature PEMs such that it had good quality. But really, during that time, the quality wasn't as important as keeping it out of the atmosphere because the material is very sensitive to moisture and heat and other things. But what I was noticing is that as we were processing, there were pinholes. There were various defects, but that wasn't my charge. And so when I came to Georgia Tech, I pivoted away from just the tooling and began to think about the fluid mechanics. And with that, that's how I won the career award. It was actually on that topic because I understood that these defects are not necessarily a consequence of the in situ performance of the fuel cell, but actually what's happening before, i.e. during the manufacturing. And so in order to increase the yield, we went on a journey to try to understand, like, how can we mitigate these defects? And if you look closely, you can kind of see some of them here. I've circled them. So the hairline fractures, the pinholes, the thinning. This thinning, hairline fractures, this is a fruit roll-up. I've had it a long time. It's brittle. I don't know if you heard this, but it just like fractured. So you can hold this, but if you hold this up to the light again, you can see these things. But maybe back there, you can actually see the change in hue. That's the thinning effect. But that leaves a gap in a space for an electronic device that then can create a short. And so we ultimately wanted to figure this out. And this is some materials that we were using from the high viscosity, high temperature PEMs down to some basic materials that we could get rid of, that we could just use as superficial materials like blackstrap molasses. This one actually got us in trouble. EH&S came to the lab and told us we can't have food. We're like, we're not eating it. We're using it to coat and to process, to understand things. And we also did the low temperature versions too with Nafion. For whenever we're processing these materials, the things that are important for us is truly understanding the surface tension, contact angle, and the rheology. Because this is a shearing process, the viscosity will change over time if the materials are non-Newtonian. But we hope that in some of the regions, we can find like some Newtonian space. And if we can, then that's the shear rate that we try to aim for, just so we can prevent changes in the rheology, which means we're not in control of the process as much because it's flowing faster or slower relative to the shear inside. This is an image of the setup that's in GTMI, our lab scale roll-to-roll system. This is about 2 meters this direction, 1 foot into the depth. And then the thickness doesn't really matter because the thickness is going to be based on what you coat and deposit on top. The slot die sits here, and this one is the 4-inch die that actually went around the room, and it can create like these nice structures here, as you can see. And I believe that's blackstrap molasses. So when people ask, what can we process? We say anything. We'll try to process water if you give it to us. Some of the nomenclature, this is the flow rate. So this is the fluid being pumped into the orifice. This is the standoff height. If you're looking at the base of that die, the standoff height, these are the contact angles that matter. 2 are static, the 2 at the top, but the one at the base is dynamic because the fluid is literally moving up, forward and back, depending upon the flow rates. And then the substrate speed, U sub V, is the substrate itself moving. And so here, this is our substrate. It's pulled up, over, and it's taken up over here. And then we have the computer system to allow us, to capture various images that you will see shortly. I talked about the coding window a little bit. Can you hear me? Yeah. Okay. So here. So the coding window sits here. This would be the range or the area in which the material is coated well, and it should be pristine, no defects. Outside of this window, either I'm pumping too much fluid and I get an agglomeration of fluid on the back side of the die, just kind of flowing, and that could lead to spreading, and so your material is not going to be in the shape and form that you would ideally want it to be in. Is this better? Is this better? Okay. Then, if your speed is too high, then you're dragging the fluid too fast relative to the pump, and your dynamic contact line shifts. And that shift is what's creating the onset of defects. For example, the air getting dragged in and the pinholes that are subsequently formed, or holes. And if you go super fast, then you'll get break lines, which look like streaks down the center of your, down the center of your material that's coated. And then the air bubbles. From a commercialization standpoint or industry standpoint, this is the line that they care about, that low flow limit. Why? Because this is controlling how fast I can make the material with said quality. This line here can technically be pushed out some. Why? Because it's based on defects that affect the performance of the device. So some devices may be okay having a few air bubbles entrained because I'm not compressing it and there's no crossing of gases or what have you. Whereas others, if I go past this point, then I would have a problem. And so we're trying to figure out what's that boundary for a variety of different materials. Again, we do computational analysis as well as experimental. And so I'm going to show you a comparison. These are some of the boundary conditions and governing equations that we look at whenever we're doing this work. So we have two phases. We have the air, and then we have the solution. We're considering the effect of wall adhesion, surface tension, continuity, momentum, volume of fluids, and then the average property values. So with this set of equations, what we can then do is compare, because think about it, you can't do experiments indefinitely. So we need to come up with a framework where we can actually test at the highest speeds possible, but know that our data is accurate. So if we position the experimental results to the numerical results, what we found is that whenever we have certain conditions, so for A, we found dripping. So this is the center between those two plates, the fluid coming out, and you can see it comes out and it goes backwards instead of being pulled forward. It did that for the experimental data as well as the numerical data. Then for B and E, we see that the contact line here, it's kind of just behind the deposition region here, and it's stable. There's no defects. The material is pretty pristine in both cases. And then we have the C and F, where we began to see this structure we call a sawtooth formation. And when we see a sawtooth formation, this may or may not lead to an actual air bubble being pulled in, but it's definitely the critical boundary. And if you go any faster, you're gonna get some kind of air bubble. Does it collapse? Does it stay entrained? That just depends upon the material. And we've seen it in both cases, where it's engulfed but not entrained, or where it's entrained and it's persistent in the material. And again, we saw this for both the experimental and computational analysis. So we know we have a great framework here. So then my student, what she was able to do is create a semi-empirical model by fitting the data that allows us to quickly get to a place where we can understand what our velocity, our max velocity is relative to the geometry of the coating tool and the properties of the fluid, and then a flow rate. And we applied this to some membranes. This is the high temperature membrane here, and as you can see, it actually has a cap, because what we found is that for this material, it's highly viscous. And unless we applied heat, we were not going to be able to reduce the viscosity, but our goal was to not use heat and make it as sustainable as possible and not add any more energy or cost to the manufacturing process. But what that means is that we're limited in space. But the good thing here is that our predictions were very accurate within, I believe, I was going to say 4%, but 5%. 5% accuracy by applying the model to the experimental data. This cartoon here just kind of shows that sawtooth formation and how it continues to grow. And ultimately, there's a pinch point where you actually get the release and the break of the bubble into the film. So these film here are all just standard solutions, nothing extra. But we then took that material, not the one that went around, but similar to the one that went around, and we measured the pinholes and the air bubbles that were present so that we could get an idea of how large they were and begin to create artificial ones so that we can test. Unfortunately, whenever you're processing materials experimentally, you're not going to get the same defects that show up at the same points every time. And so we wanted a more controlled study with NREL to do this testing. So we made artificial and real samples. And what they have is this segmented cell that has 121 unique points where they can test the fuel cell literally 121 times in one plate. So one fuel cell tested 121 times simultaneously. And since we knew where the various defects were, we could actually then figure out what the influence is. And what we were finding is that if you have air bubble, these are air bubbles, this is a crack, and this is an air bubble as well. But let me see, this one is smaller. So these are two large and one small. And as you can see, whenever you get to the transport region, you do get some dissension. And at the activation region, you get some dissension for multiple bubbles or the larger bubbles, which means there's a sensitivity. So now we can begin to think about predicting the life of the fuel cell because we know how well it's going to work or not work relative to the defects that are present. And in some cases, it was relatively stable. We took this work a little bit further to try to understand, but when is this really happening? So if we just take the one air bubble here, one air bubble at the top, and look at what happens to it as we go from a high current density to a lower current density, we see over here that there are impacts. So this is the current density, this is the impact, and this is the sample. At the lower regions, or the lower current density, we see it has more losses. But at the higher current densities, it's actually operating well. And so what we learned from this is that if we are operating with high current densities, then there's limited to no effects in terms of the defects that can be present. But they're more prominent in the low current density region. So in summary here, we found that not only can we process the material, we can process it well, and when we do, it's fine. But whenever we're out of the bounds, we will get some deterioration, but it's not a failure. The fuel cell is not going to just stop working, but over time, because of poisoning from peroxide or because of flooding, so you get H2O those are the two gases that are being fed. It may flood, so you get those kind of issues, and it continues to perpetuate. And that was the hypothesis in my career award, and that's what we proved. So we're pretty excited about this work with NREL. I'm going to shift gears quickly and go to the non-conventional slide die coating methods. This work, some of it was done in collaboration with Novacentrics. These materials are, some of them are nanocolloidal materials like PDOT-PSS. Some of them are just inks, for example, silver nanoparticle ink. I showed this cartoon earlier. We have inkjet printing, gravure, screen printing, usually to get the smaller feature sizes. So going back to the last technology, the two technologies that we developed, you can see we want lines, printed lines. And if we could get them in different orientations, that would be great. What we would overcome is the complications of inkjet. So it drops, and you have a relatively rough surface. And the question is, how can we make that smooth? We can make that smooth by having a continuous process. Gravure, it has similar challenges. And then screen printing, of course, you have the line in the screen. That's going to be prohibitive. If that's the shape you desire, then no problem. And then with spray coating, you get this plume, which means your thickness, it varies across where the material is actually sprayed. And so if you're trying to continuously spray, you're going to be building up and stacking. So again, you'll have a rough surface. So with this work, our aim was to say, okay, we can get stripes of one material, we can get patches, which are both great. Both come with these challenges of edge effects and leading edge effects that maybe we will or maybe we won't be able to overcome. But that's inherent to the process. So these are the technologies that we're going to use. I'm going to call this one coating on demand, and we're going to call this one the multi-inlet. And I'll try to continue to use that terminology because at this point we call it co-deposition, but these are a little bit dated. Let's see. These are the materials. So we're using PVA, PDMS, PDOT-PSS, and then some oils for this work. Just to orient you, sometimes whenever I'm showing you these images, sometimes we're going to be looking up into that gap like we did in the previous slides, but sometimes we're going to be looking at it from the side, so as though the slide die is laying down and we can see it straight across. And we have transparent platens in order to do that. So the tooling here, it would not be metal. It's actually made out of acrylic so that we can see and observe what's going on. So our first set of patterns are these. So the low-hanging fruit, let's just make a line as small as possible continuously. And then look at the difference between what's desired. So WO would be the actual cutout, and W is what's actually laid down. So we're going to look at the relationship and the ratios of this. In another study, we wanted to see how quickly we could turn it on and off, and what happens with the leading edge and the trailing edge. Can we mitigate the effects of this? This one is kind of like a comb structure. So if we're on, and then we turn it off and break into individual lines, we want to see that pattern, and then stir stepping. Because if we could do all of those, we knew that we would be able to make a lot of different patterns, and we would be able to make them quickly. This is what we found. So looking at the flow rate, we non-dimensionalized several things so that we could do this study. So the flow rate is non-dimensionalized against the flow rate that's pumped in, the velocities, the gaps, and the widths. And then we have the coating width. Again, that's what's actually coated, and this is the tooling opening, so between here and here. And then Reynolds number. And Reynolds number is essentially giving us velocity for this particular work. And what we see is that, and ideally, everything is like around here, but it's all over the place, right? These are different materials. So we have different standoff heights, we have different surface tensions and contact angles for all of these materials. And what we know from this is that there is a huge sensitivity. So our deposited lines, they can be wider, they can be more narrow, or they can be on the dot. And so the process sensitivity is high. The wettability is high as the viscosity goes down. And if we look at it from the Reynolds number, so thinking about process speed, then it becomes even more interesting because we don't have as much scatter. All of a sudden, things begin to collapse in these lovely groupings, and you can see that there's little to no change relative to the material property groups, subgroups. And then here we have the viscosity, but with the viscosity we see larger changes, and this is the P.PSS. It was, the scale was too different for us to put it here, and so it has its own unique set of properties, but we see that it's still sensitive. As we increase that speed, you get more dissension. Here, you get less. So going a little bit further, if we now take a step back, we have this single material that we're coating, and we're taking it on and off. We have our leading edge, our trailing edge. We want to stop very quickly. So this one is being fed through the orifices, and then this one is actuated at the base. What we show here is that depending upon how the fluid is flowing in, we get more or less taper in terms of the length of the taper. So that trailing edge is more prominent whenever we use MIF, and it's less prominent whenever we use PAF. And that makes sense. Why? Because in this case, the fluid literally has to go all the way down. So once I pinch this and stop flow, the residual capillary forces are not going to keep it in. So it's going to continue to flow later. Over here, because the on-off is at the base, we can quickly turn it on-off, and it stopped more abruptly. I have to get used to this. So on-off, you can see this is on actuation, off actuation. The bead is growing, the bead is coated, and it's wide and it's stable. The bead is wide and stable, but then you get this large trailing edge that continues until the residual is gone. Then looking at that comb-like structure, what we found here is that as the actuation is on and off, it really had a sensitivity to H, the gap between the dye lip and the substrate. And what we found that if we increase the viscosity, the surface tension, and H, then we got distinct lines. However, if we increase Q, the fluid would come back together. And so we understood from that, okay, if we control Q1, then we'll get a split, but not just Q and H in concert will allow us to get the distinct lines again. So we think about it, we're trying to go from wide area, high Q, to individual stripes, high standoff. So is it possible to get the design we want? Yes, but it would take more innovation because we would need something that's automated. So if anyone's doing automation, this would be a great space where we could actually control the patterns of the fluids that are coming out in a real way and in an interesting way. This is the actual sheet that we could create with the tooling that we have. You can see this is the wide area, and then this is the comb-like structures here. So we proved that it could work, but those trailing edges are just kind of giving us a run for our money. Stair stepping, this one was a little bit more complicated, but again, We were able to do some asynchronous work and get a coding, no coding, but trailing edge visible, another line, and then this one goes off eventually, but this one is coming on. And so we could get the stir step a little bit, but from a patent standpoint, that's a lot of bit. We've proven the concept. So we can do it. But again, more work's needed. And I want to quickly go to this part of the slot die coding process because this is the one that we found to be most desirable and of most interest because we can do more with it. If we could just figure out, like, one, how to turn these on and off quickly and maybe get something at the base to quickly pull the fluid away that's residual to mitigate the trailing edges, then we'd be okay. But here we can get multiple materials, unlike the other one. So we want to see how small of a feature we could actually get while still having a stable coating. I don't know if this video is going to work, so I don't want to risk it. So I just won't play it. But you will be able to see that the fluid's coming down, it's coming on and off, and it's creating a nice coating bead here. I mentioned this a little bit earlier. This is another way to coat multiple materials. It was developed in like the late 1990s, and you can have stacks. So OLEDs, for example, could be, this would be great for processing those. But a crossweb, that didn't exist. And again, we hold IP on that. Let's see, because I don't think this is gonna play, but I will try. Nope, and that's what I thought. So we won't play it. So here we have the outflow regions, and you can see distinctly that we have two visible fluids alternating across the web. And I have a sample for that as well, for those who wanna see. So this one with defects, this one, that's an artificial defect. It's just fractured from being handled. Oh, where did I go? Okay. So with that, now we are looking at something else, going back to those two processes. This is a single fluid, and what do we see? The shape or the pattern relative to our standoff height, we get a lot more variation. The stripe, it widens as the height decreases, which makes sense because we're compressing it, so it's spreading. And it gets more narrow as we increase that standoff height. But whenever we go to two or more materials, look at what happens. It's like no impact. So we can process more stably. And so we're looking at two different flow rates. So the flow rate is negligible in this particular case in terms of the change in width and H. And so we believe this is due to some scaffolding effects that we get. And so all of a sudden, we can process materials without having to tune them or alter them. We can process them in their real states. So again, this is showing more of the same, where we have, again, a single fluid that's coated, and whenever you increase H with increasing V, you can see there's a shift, a wide range. Whereas here, again, no effect. So we know that we're onto something very, very interesting, and we can begin to create and tune our structures to what we want them to be. And we can determine how wide each of those features are. So then we had to apply it to something real. Okay, you play with this stuff, no one's gonna use it. Who cares about PVA? No one. But P.P, well, not no one, I'm sorry. There are people that care about PVA, and we do too, obviously, because we use it a lot. But we wanted to use some more functional materials. And actually, I could blame the journal, because when we submitted the journal with PVA, they didn't like it. They wanted something more functional. So here's functional, P.PSS. And as you can see here, we have, this is about 500 microns for those who are in the back. We have PVA as the, we'll say, scaffold material. And while you get a little bit of spreading and mixing at the interface, you have a distinct line here. And then here, it's a little bit more spread out and more flat, not as concentrated, but it is still distinct. And so we felt strongly that, okay, we can process this material. Depending upon the processing conditions, we'll get a little variation in terms of the density of the fluid in the core region. But what we needed to know is, will we get some kind of conductivity out? And we did. And some in the room who's in this field, you may say, but that's low, but not technically. We did nothing to the P.PSS except use it. And we did not alter the substrate, which in this case I believe is PET, which means we took a material that's non-wetting and coated it in a way where we got distinct lines and a readout of like the functionality of that material. And relative to what we would expect, this is technically high whenever you don't alter P.PSS at all. So this is what allowed us to get our publication out, because we proved what we already knew, is that this can work. But beyond that, we proved that we can actually process non-wetting materials. Then, in the name of nano, we have this deposition here. We went to Novacentrics, and this is where we worked with them. And they have an instrument that's called a photonic curing system. We have a couple of those on campus. These systems allow for rapid solidification of a mixed material. So you can have metals and polymers in the same space. And because, I don't want to lie on their platform, but because of their technology, you're able to literally dry in line very quickly both of those fluids simultaneously without damaging one or the other. And so similar to what we did with the P.PSS, we found that with the silver nanoparticles, the problem was, what do we scaffold it against? We couldn't use PVA. It utterly failed because of the interfacial tension and various other properties. And so we had to shift to a PVP. And once we shifted to PVP, you can see it's even more stable than the P.PSS. And this coating is about 40, I think, was this one 40? Yeah, 40 microns, roughly, maybe a little bit less. That is the smallest feature that we know of using a slot die coating process. And it's stable, which means the reason why this has less spreading is because almost immediately after depositing, we were drying. Whereas with the P.PSS, we didn't do that. And so that's once it reached steady state. So adding another layer to our coating system, like this pulse forge system, we can get even more complex structures, shapes, and chemistries and process them continuously and control the feature size. So we went one further, and this is showing the difference between feature sizes here as a function of Q. So here we have much wider, and then we decrease, and as you can see, increase, and the lines get more and more narrow. Pretty awesome work, if I don't say so myself. And so with that, what we were able to show with our new technologies is that we can control shape, structure, pattern, and feature size, depending upon the implementation of the tooling that is used. We can maintain the quality as long as we continue to meet the balance between the flow rate and the substrate speed. And yeah, their nanomaterials can be processed using these methods, among others. And I want to leave you with this. Georgia Tech is, we're in the final stages of procuring and implementing a pilot scale facility This facility will have a gravure printer, inkjet printer, and slot die coating all in one, all in one line here. And so imagine the gravure here, the inkjet, and then slot die coating. It has up to 9 meters of heating, but this pilot scale system will allow you to process at speeds up to 120 meters per minute, but no one's gonna process that fast unless you have materials that dry instantly. Then okay, and I'd love to see it. But otherwise, you'll probably be more looking at pilot scale, you might reach 30. And that's still very, very fast. But I don't recommend starting here, but I do say, come by, come use it. It's gonna be a shared facility that's open to the public and of course open to everyone at Georgia Tech. And with that, I will say, thanks to a lot of funding agencies, my group, which is composed of undergrads, grad students, postdocs, and every once in a while a high school student, and various collaborators that actually worked with us on this work, especially at NREL, and then Tom Fuller here. Any questions?
Questions, comments? No, we're recording. So.
Thank you. In the multiple material coating, can you please tell us what's the minimum length you can achieve? Minimum, and if they have overlap or not. Mm-hmm. Thank you.
So, minimum width or length? Width. So the minimum width that we've gotten to is, again, somewhere between 40 and 25 microns. But the limitation there is technically our ability to cut, because there's some cutting operations beforehand, and the vibration in our roll-to-roll. So we believe once those are mitigated, we can go even finer and smaller. In terms of the mixing at the interface, sometimes, depending upon the materials and their miscibility, you may get, more or less mixing or spreading at the interface. So you see with the silver nanoparticles and the PVP, there's little to no mixing. But with the P.PSS, you can see it a lot more. So I don't know if you can see that. I can see it pretty clearly up here, but this is more manila than this region here. So this is the PVA, this is the mixed boundary, and this is the dense P.PSS. And the spreading of this region is contingent upon the rate at which we're processing and that standoff height, the gap. So it's material dependent. Oh, yes. Everything we do is material dependent, which is why we keep having to do it. Keeps us eating a little bit, so it's a good thing. Thanks. You're welcome. And I'll build more on that. So we work with a variety of different people, and we may work with one fluid. I think this is published, yeah. So RGO, we work with reduced graphene oxide. So the reduced graphene oxide that we're using, sometimes it's in one form and everything's working, but then an additive is added. And guess what? The models completely fall apart. We have to start over from square one, going from the surface tension, the contact angles, revisiting the coating window in order to find a space at which we can coat. So any little change is technically new. If it's changed to the material, it's a change to the process.
Thanks, Tequila. I really enjoyed the talk. I have a lot of questions, but one, I want to ask about the standoff height and sort of two things about it. How do you control it? And does the parallelness of it relative to the substrate, and how are you controlling that? How much does that matter, and how are you controlling it, basically?
Okay, yes, it matters a lot. So for the lab scale system, let me see if I can get there quickly. So for the lab scale system, this cross member, we have like a crank that we can go up and down. We use filler gauges from the left to the right of this to ensure that it's flat, because if not, and you have an offset, that means your gap here is higher, this is lower, this is more constrained, which means you're gonna have more spreading. Over here it's gonna be more narrow, and you won't have a uniform film. And it'll be very evident. So we've seen film where we can have defects along one side and none on the other side, only because of how the actual slot die is mounted to the equipment. For the pilot scale system that's coming, all of it is automated. Yeah, so much better.
You just did it once and fix it. It's not.
Oh, no.
Well, I mean, during a run.
Oh, doing a run, yes, yes. I was gonna say, no, we use different tools, so technically it's on and off, but yeah.
Hi, that was a very nice talk. So when you were talking about the multi-coatings, do you need to have same viscosity of the two, or can you have different solvents as well?
Mm-hmm. So yes, and
Yes and yes.
no.
Okay.
I think yes and no. So the materials do not have to be the same. The solvents do not have to be the same. Each material is going to have its own unique coating window, right? So processability window. So what we need to know is the target thickness, and the flow rate for each of those fluids is going to match to the desired thickness, because it's still pre-metered. One of the biggest constraints is that you cannot have two materials that are not miscible. If the materials are not miscible, then this process does not work. Other questions?
Any last question, comment?
So I'm a professor, so I have questions. Does anyone see value in this work with their work? Meaning, if you think about moving your work from lab scale to something more commercial, could this be some technology that could be used? I see a hand or two. Good. So then let's talk, because maybe there's opportunity for collaboration. And if you're seeking advice regarding the processability of your materials, of course, you can ping me.
I just have one more question. Mm-hmm. So are you limited to only like polymers? I mean, the roll-to-roll, or
Very good question. No, we work with a variety of different materials. Again, we work with inks, we work with colloids.
Oh, sorry, I'm talking about just the substrates.
Oh, substrate. Oh, that's even better. I had some other substrates here. No, we work with porous materials, and these porous materials can be like continuous, like the paper, the carbon black paper. We have wovens that we use to create composite structures. We coat on film, like on thin metallic film, and we also process on glass. With the glass, I mean, it's a little tricky. It's not going to be roll to roll. It's going to be more sheet to sheet. But if you have willow glass that's flexible, then we could begin to explore roll to roll on flexible glass.
I was going to ask glass, but you already answered it. Thanks.
Yes.
All right, I think we're at the top of the hour, so let's thank Professor Harris one more time.
Thank you.